Neural networks are currently being pushed to solve mathematically impossible tasks, but there is a massive catch. The data we feed them is mathematically rigged. 94.2%. That is the test set accuracy achieved by a long short-term memory network on a notoriously difficult NP-hard computer science problem. A score that high strongly suggests the model actually cracked a computationally intractable puzzle. We're talking about the exact kind of problem that normally breaks supercomputers and halts traditional algorithms in their tracks. Hitting 94.2% implies the network somehow learned the fundamental logic of the problem and can now solve fresh, unseen instances with near-perfect reliability. But it didn't. The model did not learn the problem. It just learned the dataset. By feeding these networks millions of generated examples, we are accidentally teaching highly capable Turing-complete architectures a completely different, significantly easier task. It's a fascinating misdirection, and understanding how it happens exposes a massive blind spot in how we train modern AI. At an industry scale, modern neural network architectures, like recurrent neural networks and LSTMs, are remarkably expressive. Researchers are deploying them against massive, real-world logistical and mathematical challenges. Think about the traveling salesman problem, optimizing supply chain routing and delivery fleets across thousands of global nodes. Or Boolean satisfiability, a foundational logic problem critical for software verification and hardware design. The core bottleneck in these efforts is not the artificial intelligence's capability to process information. It's not about finding hidden patterns. The actual bottleneck is data generation. Deep learning requires massive, dense, unbiased data sets to learn effectively. Finding millions of labeled, correctly solved examples for computationally hard problems is a massive, often insurmountable logistical hurdle. To get those millions of necessary data points, practitioners rely on tools called polynomial samplers. These are essentially algorithms that generate labeled data points in polynomial time. They make the creation of massive training datasets feasible, churning out thousands of complex, nested JSON data objects per second, filled with pre-computed query vectors. You just start the script, and within hours, your hard drive is absolutely full of training data, neatly labeled and perfectly ready to feed into a PyTorch or TensorFlow model. It feels like a silver bullet. The mathematical mechanism at play here is actually a trap. If you generate a truly NP-hard task, you are operating in a vast, highly complex space. But the moment a polynomial sampler outputs data, it lands squarely in a vastly restricted subset. Here's the part that's easy to miss. By definition, if you generate data fast, in polynomial time, you mathematically trap the resulting dataset in a simpler subproblem space. Specifically, this is the intersection of NP and co-NP. You aren't sampling the whole difficult space. You are generating a highly specific, restricted subset of the problem that completely lacks the complexity of the original task. To map this abstract math to a physical space, the real NP-hard problem is like being asked to sort every single book in a chaotic, infinitely expanding library. Doing that requires immense time and complex logical rules. The sampled subproblem, the data generated by our fast algorithm, is like only picking the books that have uniformly red covers. Any fast data generator bypasses the actual hard problem entirely. It feeds the network a superficial pattern, which the network then happily optimizes for. A neural network trained only on picking out red books would be completely useless if you suddenly asked it to organize the rest of the library based on author, subject, or publication date. It completely ignores the complex logic we actually wanted it to learn in the first place. A skeptic at this point would reasonably ask a very simple question. If fast samplers ruin the data and create superficial subsets, why not just use the slow, accurate, deterministic solvers to build the dataset in the first place? If the fast way is flawed, simply use the slow, correct way to build the dataset. It seems like the obvious fix. The trade-off is hard physics. Generating millions of accurate data points with exponential time solvers is physically impossible for large inputs. Because the runtime of these deterministic solvers grows exponentially with the size of the problem, scaling up isn't just a hurdle, it's a brick wall. Getting the 15 million samples needed to adequately train a modern network using a purely deterministic solver wouldn't just take a few weeks on an AWS server farm. Due to thermal and computational limits, it might literally take longer than the universe has existed, which frankly is a tough timeline to explain to a project manager. We are forced to use fast, flawed samplers because the correct samplers are fundamentally constrained by time itself. Conjunctive Query Containment, or CQC, serves as a perfect, concrete case study for this phenomenon. It is an NP-complete database problem that asks if the results of one database query are entirely contained within the results of another for every possible database state. If an AI could solve CQC instantaneously, it would completely revolutionize how massive cloud architectures cache and retrieve data, verifying data integrity in real time and saving millions in raw compute costs. It is exactly the kind of highly complex, highly valuable problem that engineers want deep learning to solve. Researchers built a rigorous, modern setup designed to succeed at CQC. They encoded the database queries into 42-dimensional one-hot vectors across a sequence length of 95. The architecture maps these into an LSTM output space of exactly 256 dimensions. The network is then optimized via the Atom optimizer, tuned with a learning rate of 0.00105. This is a standard, highly robust deep learning pipeline. It is fully capable of recognizing intricate patterns across complex sequences, given the right computational budget and memory constraints. To get the necessary data without waiting billions of years, they employed a very specific data augmentation strategy. First, they generated a very small seed set of queries using a slow, deterministic tool called the vampire theorem prover. Then, they applied class-preserving rewrites sequentially to scale it up fast. They executed commands like --merge var to collapse variables, --split var to divide them, or --add conj to inject a new conjunction entirely, all while maintaining the underlying Boolean label of the query. Worth sitting with for a second. This linear scaling strategy successfully inflated that tiny seed set into 15 million distinct training samples, completely sidestepping the exponential time trap of the deterministic solver. The training run over those 15 million samples produced a pristine optimization curve. Validation accuracy climbed smoothly past 90%, while cross-entropy loss steadily plummeted. By all standard empirical machine learning metrics, the LSTM completely succeeded. It looked at 15 million augmented examples and seemingly mapped the intractable logic of conjunctive query containment, achieving a state that would normally indicate genuine algorithmic understanding. Then came the reality check. The researchers took the trained model out of its augmented sandbox. They tested it against all-cqc.csv, a monstrous file containing over 537 million real, unaugmented query pairs that were deterministically labeled. They also tested it against a separate dataset, mu10.8, containing 250,000 balanced queries, generated entirely outside the original augmentation bubble. These test sets represented the true breadth of the NP-hard problem, not the narrow subset generated by the fast sampler. The empirical proof of failure is stark. That beautiful 90% training illusion is completely undercut by the reality of generalization. Accuracy on the massive all-CQC dataset dropped to 80.4%, which is actually worse than it sounds because that specific dataset is unbalanced. Simply guessing 0 every time yields over 90% accuracy on that set. On the balanced, unaugmented mu10.8 set, accuracy plummeted to 64.7%. The model spent hours of GPU compute learning a superficial structural cheat within the augmented data. It is the architectural equivalent of training a massive Turing-complete AI purely so it can check if the first bit of a text string is a 1 or a 0. The authors of the study, Gal Yehuda, Moshe Gabel, and Asaf Schuster, summarize the current mathematical limits of our data generation tools with this statement. It's not what machines can learn, it's what we cannot teach. The neural networks themselves are highly capable, but our methods for providing them with the necessary curriculum are fundamentally broken when dealing with computationally hard problems. This establishes exactly where things currently stand. Deep learning models learn the data generator, not the underlying problem. Purely supervised learning, which relies on dense, uniform samplings of data, hits a hard mathematical wall when faced with NP-hard tasks. But this is a highly constructive realization. The future involves hybrid differentiable systems. We have to stop trying to force the network to blindly guess at impossible logic and instead integrate hard-coded, deterministic solvers as actual routing layers within the network itself. We stop trying to teach the network the impossible and start giving it the tools to calculate the answers directly. That initial 94.2% score is not a triumph of machine learning. It is a glaring symptom of flawed data. The number reflects a model perfectly mastering a compromised test. Are we teaching machines to solve the complex problem, or just teaching them how to ace our specific flawed test? Please note this explainer is drawn from It's Not What Machines Can Learn, It's What We Cannot Teach by Gal Yehuda, Moshe Gabel, Asaf Schuster. Informational only, not advice. If you enjoyed the journey, a share or a subscribe goes a long way. Thanks for watching. See you in the next one.